Hello everyone, welcome to excellent series of lectures where we complete your course with respect to your boards JEE as well as NEET. Dear student, this is Sagar, the Regiochemistry teacher, and as you all are aware that we have already started a chapter called as Haloalkanes and Haloarenes. So I welcome you all in this series of lectures, that is excellent series towards the organic chemistry. Well guys, so you all are aware that it's been 2 sessions that we have been learning haloalkanes and haloarenes. Precisely speaking, we are studying reaction mechanism. So far in this chapter what we have studied, I'll just brief and then we'll see what exactly are we going to learn in our today's class. So prior to this, we have studied the types of reagents, followed by we also saw different types of solvents. Then we studied the impact of solvent on the nucleophilicity, followed by different leaving groups and how to identify if several leaving groups have been given, their order of leaving group abilities. While in class number 2, we actually started learning the reaction mechanism. We picked the first subtopic, that is nucleophilic substitution reactions. And with respect to this nucleophilic substitution reactions, we studied 3 mechanisms in detail. That is bimolecular nucleophilic substitution reaction SN2, unimolecular nucleophilic substitution reaction SN1, and we also covered neighboring group participation. So dear students, in our today's class, what exactly are we going to learn? Let me show you. So our today's learning objective would be to study elimination reaction. So as far as elimination reactions are concerned, again we will be learning 3 important mechanisms, that is unimolecular elimination reaction E1, followed by bimolecular elimination reaction, that is E2, and with respect to E2 we'll also be discussing Sedzev and Hofmann elimination. Then we'll also be discussing substitution versus elimination, and once that is done we will be learning yet another important mechanism called as unimolecular elimination via conjugate base, which we call it as E1CB. So guys, without wasting much of a time, let us begin with the elimination reaction. Just a brief introduction. When we talk about elimination reaction, as the name itself suggests that we are going to carry out elimination of an atom or a group of atoms. So since we are learning this reaction with respect to haloalkanes, or you can say alkyl halide, you will generally see that the halogen atom acts like a leaving group. So from a given alkyl halide, when there is removal of halogen atom as a leaving group, at the same time there is a removal of proton as well, then such type of reactions where halogen atom and hydrogen atom have been eliminated from a substrate, resulting in the formation of alkene as your product, in general you call it as elimination reaction. Further, when we talk about elimination reactions, this elimination reaction can be of several types. That is alpha elimination, beta elimination, or it could be the third type called as 1,N elimination. Now what does exactly this means? Look, the most important type of elimination out of this as far as our studies are concerned is the beta elimination. Hence we are going to learn in detail the beta elimination, but let me just brief you about alpha, beta and 1,N elimination. See, as we have mentioned that in elimination reaction, we carry out removal of halogen atom as a leaving group and hydrogen atom. If this hydrogen atom and halogen atom have been eliminated from the same carbon atom, we call it as alpha elimination. But if removal of halogen atom and hydrogen atom takes place from the adjacent carbon atom, we call it as beta elimination. And now imagine, if abstraction of a proton, that is removal of hydrogen, is taking place from the carbon which is far away from the carbon carrying leaving group, that is halogen atom, then such elimination can also be referred as the 1,N elimination. Out of which, as far as our syllabus is concerned, dear students, we talk about beta elimination. So let me show you beta elimination here. Well, so you can see we have got some substrate. We have got ethyl chloride. We are allowing this ethyl chloride to react with the base. Now to understand, a carbon carrying leaving group is the alpha carbon, and the carbon adjacent to alpha is what we call it as beta. So let's say we have got a strong base, and this base abstracted hydrogen atom from the beta carbon. Upon loss of this hydrogen in the form of H+, the sigma bond shifted further, which in turn eliminated the halogen atom as well. So the product obtained here is CH2 double bond CH2, which is nothing but an alkene. Now this reaction clearly indicating that the loss of halogen atom and the hydrogen atom is taking place from the adjacent carbon atom. So we call such type of elimination as beta elimination. Sometimes it is also referred as 1,2 elimination. These beta elimination reactions are of two types, that is unimolecular elimination, that is E1, and bimolecular elimination. Alright, and other than this we also talk about E1CB, unimolecular elimination via conjugate base. For the timing, let's first learn about E1 elimination. Well guys, I don't want you guys to look at everything at once. Again, whenever you're learning E1 reaction, always try to keep a reference of SN1. So in the previous class we discussed about SN1 reaction mechanism, right? What were two important features of that reaction? Number one, SN1 reaction mechanism takes place in two steps, right? In which first step is a slow dissociation of a carbon halogen bond resulting in the formation of a carbocation. And formation of carbocation, we call it as the key feature of SN1. So dear students, even E1 reaction, that is unimolecular elimination reaction, follows the same order. That is, even in case of E1 reaction mechanism, it's a two-step reaction, where in step number 1, there is slow dissociation of a carbon and a leaving group bond to form a carbocation. Alright? Now once carbocation is formed, then the weaker base abstract the beta hydrogen atom. Hence even E1 reaction is the two steps reaction. So let us try and understand the E1 reaction. Like we said, the type of beta elimination which takes place in two steps is your E1, unimolecular elimination, in which step number 1 is slow dissociation of a carbon leaving group bond to form a carbocation, and second step is a loss of beta hydrogen atom towards the base. And as we have seen that in case of SN1, solvent itself was acting like a base. Here as well, solvent itself will act like a base. So such reaction we refer it as even reaction. Now several times it happens that the nature of substrate, the nature of base, then the solvent, everything will look exactly similar to that of SN1 reaction. So if you compare SN1 reaction conditions and even reaction conditions, they are going to be almost the same. The only factor that differentiate between E1 and SN1 is nothing but the temperature. So I want you all to remember that E1 reaction occurs at higher temperature. So rest everything in most of the case will be identical. It's just that E1 reaction will take place at a higher temperature. And that's why let us consider one simple reaction. So guys, what we have got here is tertiary alkyl halide. Again, we have got highly substituted alkyl halide. So carbon carrying leaving group is the alpha, adjacent carbon is beta, so we have got beta carbon here. If this is beta, even this is adjacent, so even this can be called as beta. But because both are equivalent, I am highlighting only one of the beta. But on the other side, I have got yet another beta carbon atom which is different than this beta. So let's call it as beta dash. And now we have taken this alkyl halide to undergo even reaction in presence of water, which is going to act like a weak base. So solvent itself is going to act like a base, and we allow this reaction to take place at relatively higher temperature. Now sticking to the basic definition of even reaction, which says when the abstraction of hydrogen takes place at the beta carbon atom, meaning carbon adjacent to the carbon carrying leaving group. So here, since we know that we are going to carry out elimination where halogen will be removed from alpha carbon and hydrogen will be abstracted from the adjacent carbon, that is beta. Now because I have got two different beta carbon atom, meaning two non-equivalent beta carbon atom, there are two products expected. Imagine if hydrogen is abstracted from the beta dash carbon and also loss of halogen taking place from the alpha carbon. So we will be getting formation of double bond over here to result in the formation of product, that is 2-methyl-2-butene. Well students, we aren't learning mechanism yet. We are just trying to understand the simple reaction. Okay, so I'm directly considering the product. Similarly, if loss of beta hydrogen takes place from this lesser substituted beta carbon atom, then you will see the double bond formation will take place between first and the second carbon, which is right over here. So I have got two elimination product because I had two non-equivalent beta carbon atom from where hydrogen could be lost. Now the two product obtains, if I want to find out which of this is major product and which is minor, we simply talk about the stabilities of these two products. So two alkenes can be compared with respect to their stabilities on the basis of their hyperconjugation stabilities. Hence, if this is the carbon-carbon double bond, with respect to carbon-carbon double bond, if you see, we have got 3 alpha hydrogen here, 3 more alpha hydrogen here, and 3 more here as well. So this alkene will have total 9 alpha H's, as a result of which it can show 9 hyperconjugating structures. On the other hand, 2-methyl-1-butene has only 3 plus 2. This is your alpha, even this is your alpha. Total we have got 5 alpha hydrogen atom. So this alkene will show 5 hyperconjugating structures, and we say more the number of hyperconjugating structure, more the stability of an alkene. So clearly 2-methyl-2-butene is more stable alkene than 2-methyl-1-butene. Because it is more stable product, this will be obtained as a major product. And let me tell you, more stable alkene is also referred as Sedzeff elimination product. So you can simply call it as Sedzeff product. Sometimes it is also known as Zetsev product as well. Sedzeff or Zetsev. On the other hand, the less stable alkene which is obtained as a minor product is known as Hofmann elimination product. So this is Hofmann's elimination product. Well, how exactly these are formed, we are going to see the detailed mechanism of this, but let me just brief you what we have studied so far. In elimination reaction, there exists alpha elimination, beta elimination, and 1,n elimination. As far as our syllabus is concerned, we study beta elimination. Beta elimination further could be E1, E2, or E1CB. We started with E1 reaction mechanism, where just like SN1, E1 reaction also takes place in 2 steps. Step number 1 is a formation of carbocation. Step number 2 is once carbocation is formed, then the weaker base, generally solvent itself, abstract the beta hydrogen atom, resulting in the formation of alkene. But if our alkyl halide is such where we have got more than one type of non-equivalent beta carbon atom, then we get more than one product, out of which the alkene which is obtained as a more stable product, which you find out on the basis of hyperconjugation stabilities, then such product is the major product called as Sedzeff elimination product, and the minor one is called as Hofmann elimination product. Now guys, let's try and understand the detailed mechanism of this particular reaction. So step 1 is we have got tertiary alkyl chloride in presence of water as a solvent, which is a polar protic solvent with a higher dielectric constant, helps slow dissociation of a carbon chlorine bond. So because chlorine is more electronegative, it will pull the bonding pair of electron towards itself, and slowly carbon chlorine bond will be in a process of breaking. Such a slow step is regarded as rate determining step. So the slow dissociation of a carbon chlorine bond can be represented this way. Let's say we have got CH3, CH2, and now carbon chlorine bond is in a process of breaking. So I'm showing partial bonding here. And up here we have got methyl. Here as well we have got methyl group. Now as you can see here, the carbon chlorine bond is in a process of breaking. This is going to be highly unstable compound with a maximum energy content. So such a state of highest energy content through which every reactant must pass in order to get converted to product. Dear student, what do we call it? Yes, we call it as transition state. Once you get transition state, because it is state of maximum energy content, it immediately loses the leaving group. So carbon chlorine bond will be immediately broken. And as soon as Cl leaves in the form of Cl minus, it will result in the formation of carbocation. So this step will now be a fast step, and that will result in the formation of tertiary carbocation. So when we're using water as a solvent, that water is not appearing in the rate determining step, meaning this clearly indicate that rate of reaction is dependent upon molar concentration of only substrate and not the base. We shouldn't be using term nucleophile here, and it is independent of a concentration of base, which means it is simply a unimolecular reaction. I'm sure you all are now able to relate it because we have used the similar term in SN1 reaction mechanism as well. Right guys? But the role of water as a solvent in this reaction is to help the dissociation of a carbon chlorine bond, and once the bond is broken, the corresponding carbocation which is formed can be stabilized by ion dipole interaction. As we know, water is a dipole, so the negative pole of water, which is oxygen, will surround this cationic carbon from all possible sides and stabilize this carbocation. And along with this, we are also getting Cl minus. Once the carbocation is formed in step number 1, in step number 2 what happens? Can you see this was cationic carbon? So we have this 2 beta carbon. This is what we had earlier designated as beta dash, and this is beta carbon. Now this water can abstract beta hydrogen either from beta carbon or beta dash. Let's say if it is attacking the beta dash, so H will be lost as H plus, sigma bond will be shifting over here. Similarly, water can also abstract hydrogen from the beta carbon atom. If H plus is lost, this can shift further in between and you'll get formation of double bond. Let's call this is mechanism path B and this one as path A. So if I have to write down the product according to path A, firstly when water will attack this hydrogen atom, there will be new bond formation between oxygen and hydrogen. So we'll have to show the partial bonding here. Because carbon hydrogen bond is in a process of breaking, again there will be partial bonding here. And since this sigma bond is shifting here to result in the formation of pi bond, there will be partial pi bond character here as well. So guys, in this step 2, we will be getting yet another transition state. And how do we show that? Look. That's CH2 here. CH and this CH bond is in a process of breaking, which is attacked by a water. Between this carbon and the cationic carbon, there is new pi bond formation with CH3 group here, followed by CH3. So everyone, this is what we refer it as transition state 2. Let's call it as TS2. And if you consider mechanism via path B, so what is abstracting the beta hydrogen atom? So the transition state corresponding to this can be represented like this. So this carbon we are keeping as it is, CH3, CH2. All right, CH3. Now look here. From beta carbon, the hydrogen is about to leave. So a partial bonding between carbon hydrogen bond, new pi bond formation between the cationic carbon and CH2, and oxygen is forming a new bond with hydrogen in order to abstract it. So depending upon path A and path B, we are getting transition state. Both will be called as transition state 2. If you see the first transition state, I mean transition state via path A, this transition state is more stable because it is developing a double bond character such that the corresponding alkene form is going to be more substituted alkene. Hence, this transition state is the more stable transition state. So, transition state 2 here is more stable. Hence, the corresponding alkene will also be more stable. Whereas this transition state is showing a partial double bond character between the carbon such that the character of alkene is corresponding to the less substituted alkene, which is the less stable alkene. Hence, we will say this is relatively less stable alkene. And eventually, because this is transition state of highest energy content, it immediately will form a corresponding product. So everyone, how are we going to write down the product? Wherever you see the partial bond in the process of formation, make it permanent. And whichever partial bond was in a process of breaking, just remove it. So the product obtained here would be CH3, CH, double bond, CH3 and CH3. So we get alkene with 9 hyperconjugating structures. And the second one over here, double bond between first and second carbon, CH3, CH2, CCH3 and double bond CH2. So guys, like we said earlier, this is the more stable alkene, right? So this is the major product and called as Setzeff elimination product. So this is more stable. Because more stable, this is also a major product. This is less stable, called as a minor product, and more stable product we call it as Setzeff's product. And the less stable alkene we call it as Hofmann's elimination product. So guys, simply what we have to understand, in most of the cases, the major product is always going to be a Setzeff elimination product. And how do we identify which is Setzeff elimination product? Well, so if you have got choices of more than one beta hydrogen atom, then removal of hydrogen from the beta carbon atom having lesser number of H will result in the formation of more substituted alkene, which is the ZZF elimination product. Or in other words, you can say that, see, this is more substituted carbon. So after loss of H plus, the carbon ion character here is going to be less stable because it is more substituted. So more plus I will increase the electron density on this carbon if we consider carbon ion formation after loss of H plus. So less stable the conjugate base, weakly acidic or lesser acidic the corresponding carbon is. So another way of defining ZZF elimination product is the product of beta elimination obtained in such a way that base abstract the hydrogen atom from the beta carbon atom which is lesser acidic, or from the beta carbon which is carrying less number of hydrogen atom, to yield more substituted product is ZZF elimination product. Whereas what is Hofmann elimination product? A type of beta elimination product where base abstract the hydrogen atom from less substituted beta carbon or from the more acidic beta carbon atom. Why is this more acidic? See, compound is acidic when the conjugate bases are stable. So if I assume after loss of H plus, the carbon ion will be formed here. So that conjugate base here at this carbon will be more stable because it is least substituted. This carbon was more substituted. Hence, due to plus I, the stability of conjugate base will be lesser. So beta carbon is more acidic. Hence, abstraction of beta hydrogen from that beta carbon which is more acidic will result in the formation of less substituted alkene. That is what you call it as Hofmann elimination product. So guys, that was all about the unimolecular elimination reactions. Well, if you again try to think about some important characteristics of this reaction mechanism, the first one, imagine if I have to write down the rate expression for this reaction. How will we write it? Well, in rate determining step, only one molecule is involved. So one thing is for sure, the molecularity of reaction is going to be only one. And the rate of reaction is directly proportional to molar concentration of only substrate. Keeping these facts in mind, let's say now if I have to write down, or I have to draw rather, energy profile diagram. So in our reaction mechanism, we started with substrate. We saw in a given substrate, step number 1 was slow dissociation of a carbon halogen bond. So the partial bonding result in the formation of transition state. So you'll see the energy will increase as the reaction progresses. So this point will correspond to transition state 1. Right, everyone? Once transition state is formed, immediately carbon leaving group bond breaks and it results in the formation of stable carbocation, because the substrate that we have taken is more substituted alkyl halide. So carbocation form is going to be a stable carbocation. So carbocation being stable, the energy will decrease. So this point will correspond to stable carbocation. Once stable carbocation is formed, now the weaker base such as solvent itself abstract the beta hydrogen atom. Now since we have got two different beta hydrogen atom, we got two mechanism path. Path A, where water abstracted hydrogen from more substituted carbon, resulting in more stable transition state 2, meaning energy of this transition state 2 obtained via path A is going to be lesser because it is more stable. So if I can see carbocations are getting converted to two more transition state, which we are referring it as transition state 2. So the more stable transition state was via path A. So this one was via path A. This one is via path B. Hence the product corresponding to the path A is more stable alkene. So this is more stable alkene. This is less stable alkene. So the alkene obtained here is a ZZF elimination product, and alkene here is Hofmann's product. and here we have got such a elimination product. All right, guys. So when we plotted energies of reactants and the product along with the intermediate against the progress of reaction, we got a curve. So the curve obtained when you plot energies of reactants and product against the progress of reaction is what we call it as energy profile diagram. And now we will be talking about the characteristics of even reaction. Well, all the important point we have discussed it earlier, we'll just write it down. Rate expression. Experimentally, we know that rate is proportional to molar concentration of only substrate. Which can also be written as rate is equal to constant K into molar concentration of substrate. That indicate by altering the concentration of substrate, the rate of reaction will also be altered. But by changing the concentration of base will have no impact on the rate of reaction, because rate expression is not involving any of the concentration of base here. So guys, rate of even reaction mechanism is independent of concentration of a base. From this we can also see because in RDS only one molecule is involved, that is substrate, we will say molecularity of reaction is 1, and in the rate expression substrate to the power nothing meaning 1, so the order of reaction is going to be the first order. So I will say it is unimolecular, or you can say molecularity is 1, and first order. First order with respect to substrate, and overall also it's a first order reaction. Alright everyone, well, so these were two important characteristics, and now we'll talk about the factors affecting the rate of even reaction. The first factor is nature of substrate. Well guys, what is the key feature of this even mechanism? The key feature is, in step number 1, there is slow dissociation of a carbon halogen bond resulting in the formation of carbocation. And whichever carbocation will be more stable, obviously the rate of reaction towards such a substrate is going to be higher, which means the substrate which we have should be such that after dissociation of a carbon halogen bond, the corresponding carbocation form should be more stable one. So what kind of substrate will result in stable carbocation? Yes, absolutely. Tertiary alkyl halides carbocation being more stable, tertiary alkyl halides rate will be faster towards even reaction, just like in SN1. Hence imagine if we have got primary alkyl halides, secondary alkyl halide and tertiary alkyl halide. If you look at the carbon carrying leaving group, in case of primary alkyl halide there is only one alkyl group present at the carbon carrying leaving group. In secondary there are two alkyl groups present at the carbon carrying leaving group, and in tertiary there are three alkyl groups at the carbon carrying leaving group. So as the number of alkyl groups at the carbon carrying leaving group increases, the corresponding carbocation form is going to be more stable carbocation, which in turn will increase the rate of even reaction mechanism. Hence tertiary alkyl halide will be most reactive, secondary is second best, and ethyl is going to be the least reactive alkyl halide, and methyl halide won't even give this unimolecular elimination reaction since its corresponding carbocation is very less stable, or you can say kind of unstable. Alright. Second leaving group. Well guys, I have told you this, right when we studied the nucleophilic substitution reactions, whichever mechanism you consider, in this all the reaction, the leaving group that we want has to be a good leaving group, because whether it is SN2, SN1, even or E2, in all the cases we want leaving group to leave from the substrate to either result in the formation of carbocation or simultaneously departure of a leaving group with either attack of a nucleophile or with the abstraction of a proton. So leaving group always has to be a good leaving group. So if you have got fluorine, chlorine, bromine and iodine, poor bases are good leaving groups. So I minus is the best leaving group, then Br, then Cl and then F. Nature of base. Okay. What is our rate expression? Rate expression is rate is directly proportional to molar concentration of only substrate. So base does not have any impact on the rate of reaction, meaning we don't need a stronger base, weaker base, meaning generally solvent itself, which act like a weaker base, will be required for even type of reaction to take place. So we say, since base does not appear in the rate expression or equation, weak base, usually solvent itself favors the even. And what kind of solvent do we want? That's going to be the next factor. Yes, we always want polar protic solvents so that it helps the dissociation of a carbon leaving group bond. Hence everyone, the nature of solvent is we need polar protic solvents with high dielectric constant like water, with high dielectric constant favors even. Effect of temperature. Well, I have told you earlier as well. If you see the condition of SN1 and even, by now we have studied SN1 as well as even. So if you see the condition of both of these reactions, they are almost the same. The only one factor which differentiates between SN1 and even is the temperature. See, in case of SN1 type of reaction, there is only carbon halogen bond is broken, and then the new bond between nucleophile and carbon is being formed. So breaking of bond involved is only with respect to carbon and leaving group in case of SN1. But when you talk about elimination reaction, other than carbon leaving group bond, there is a breaking of bond involved between the beta carbon and hydrogen as well. So because breaking of bond is more in case of elimination reaction, we need temperature, because higher temperature will favor the breaking of a bond. Hence, higher temperature favors elimination over substitution. So higher temperature favors unimolecular elimination reaction. Alright guys, so these were some of the important factors that affects the even reaction. Now look, we have always said that whenever there is a formation of carbocation, even in general organic chemistry we have learned, whenever there is a scope of formation of carbocation, we have to always understand that if the carbocation form is not the stable one, but has a scope of undergoing rearrangement and to form a more stable carbocation, then we should always carry out carbocation rearrangement first and then the next step. This carbocation rearrangement can take place either via hydride shift or a methyl shift or maybe via ring expansion reactions. So whenever we are forming a carbocation, we have to always be careful and think whether or not this carbocation is going to undergo further rearrangement. If required, we'll have to do the rearrangement first. As of now, let's have a look at some example of even reaction mechanism. So we have got secondary butyl bromide here, along with which we have got methanol as the solvent, and the heat is given. Guys, because we are learning even, now we know that even has to be carried out. But imagine if this reaction comes in general with many other reaction, we will have to first decide which reaction mechanism path this reaction is going to follow. And how do we do that? Let us do that first. So the degree of alkyl halide is secondary. Right, everyone? So this is quite favorable for E1 as well as SN1. The solvent which is given is not a strong species, everyone. This is not the anionic species. Had this been anionic, the possibility could have been SN2 as well as E2. But because this is neutral, neither SN2 nor E2 will take place. So the only two options left is SN1 and E1. So a solvent can undergo or solvent can carry out SN1 or E1 reaction mechanism. But now since heat is mentioned, we know that this is going to follow even reaction mechanism. So in even reaction mechanism, carbon-bromine bond would be broken to form a secondary carbocation. So the intermediate that we have got is CH3, CH2, CH plus, and CH3. So you can see now there are two types of beta carbon. This is beta and this is beta dash. So your solvent can act like a base and can abstract hydrogen either from beta carbon or from beta dash carbon. If base abstract hydrogen from beta carbon, you will get double bond formation between the cationic carbon and beta. So the product will be 2-butene. And if abstraction takes place from here, we'll be getting 1-butene. So two products obtained would be CH3CH double bond, CH3. Right, everyone? That is 2-butene. And along with this, if abstraction of hydrogen takes place from beta dash carbon, we will be getting 1-butene. So 2-butene has total 6 alpha hydrogen, so 6 hyperconjugating structures. 1-butene has only 2 alpha hydrogen, so 2 hyperconjugating structure. More the number of hyperconjugating structure, more stable the alkene is. Hence, I will say this is the major product. And this one is minor. Alright, everyone. Now, let's have a look at some more example here. So example number 2, they have given us some tertiary alkyl halide, and not alkyl halide, there is a triplet leaving group is present, and we know that triplet, tosylate, brosylate, all are one of the good leaving group. So because we have got good leaving group here, this is tertiary. So the probable mechanism that we were thinking, let's say SN2, E2, E1 and SN1. Now how do we finalize which mechanism will it follow? Well guys, for SN2 reaction to takes place, the nature of substrate has to be least sterically hindered. Tertiary alkyl halide does not give you SN2, so ruled out. E2, well, we haven't studied E2 yet, but E2 reaction mechanism takes place only in presence of strong bases. This is not a strong base, so ruled out. Because substrate is tertiary, SN1 even both are favorable. Because solvent itself is used as a base or nucleophile, both E1 and SN favorable. But because temperature is given, now one thing is clear, it is going to follow E1 and not SN1. So let's carry out E1. What we do in E1? The leaving group leaves first to form a carbocation. So we will be getting formation of carbocation. Now once this is the carbocation form, then in the step number 2, loss of hydrogen will take place from the beta carbon. So how many possible beta we have got? With respect to this, this is beta. So there is one hydrogen here. With respect to this, this is also beta. Let's call it as beta dash. With respect to this, this is also beta. Let's call it as beta double dash. So a removal of hydrogen from any of this beta carbon will result in different types of alkene, and whichever will have more number of hyperconjugating structures is going to be the more stable alkene. So 3 products obtained are removal of hydrogen from beta carbon. So this is the first one, and of course this is going to be the most stable alkene. Hydrogen abstraction from beta dash, which is this, and the third one. Right? So you can see here we have got 2 plus 2 4 plus 3 7 plus 3 10 hyperconjugating structure. So this is more stable. Hence this is the major product, and the remaining 2 will be the minor products. Alright guys, so that is how you are supposed to find out the major minor product of elimination reaction. Well, we are quickly going to go ahead with E2. I'll take a short break. I want you guys to go through the introduction of E2 till then. Alright everyone. Come on guys, go through this. So just like we say in case of even reaction, we can have a reference of SN1. Similarly, in order to learn E2 reaction, we can have a reference of SN2. So what were important feature of SN2? SN2 was a one-step reaction mechanism, and the key feature was it was the concerted reaction. Concerted meaning bond making and bond breaking takes place simultaneously. Exactly in the similar manner, E2 reaction is also a one-step reaction, but here abstraction of a beta hydrogen and departure of a leaving group takes place simultaneously. So if we want abstraction of a beta hydrogen, meaning removal of beta hydrogen to takes place simultaneously, we'll always need a strong base, and hence we say the type of beta elimination reaction which takes place in presence of strong bases. I want you guys to remember these 5 strong bases. Which 5 strong bases? Start with the term alcoholic KOH. So alcoholic KOH. From term alcohol, remember ethanol, and this is its conjugate base. So ethoxide ion. From alcohol, remember methanol. So this is the conjugate base of methanol, that is sodium methoxide. Just like alcohol, remember tertiary butoxide. You see this is tertiary carbon. So this is tertiary butyl alcohol's conjugate base. And finally, we have got soda amide. So the type of beta elimination that takes place in presence of strong base, such as these 5, you call it as E2 reaction mechanism. Say 90% of the question you will find, if they want to ask with respect to E2, they'll give you either of these bases. And that's why simply remember these 5 bases. Okay, which 5 bases? Remember the first one, alcoholic KOH. So alcohol is a very important term, because using alcohol you need 3 more bases of alcohol only. So alcoholic KOH, then ethanol's conjugate base, then methanol's conjugate base, then tertiary butyl alcohol's conjugate base, and finally soda amide. So to understand, let's say we have got 2 bromobutane. This is the carbon carrying leaving group, so this is alpha carbon. Adjacent carbon is beta, Even this is adjacent carbon, but different than this beta, so I'm calling it as beta dash. And I'm carrying out reaction with sodium ethoxide. Now look, sodium ethoxide being a stronger base, it will not let carbon halogen bond dissociate and then attack, because it's a strong base. So strong base will immediately attack at the beta hydrogen atom. So there are two possibilities from where it can abstract the beta hydrogen. So let's say if abstract the beta dash hydrogen, I'm calling it as path A. And if it abstract the beta hydrogen, I'll call it as path B. Whichever H is being removed, after loss of hydrogen, sigma bond will shift, and there will be simultaneous loss of the leaving group. Guys, this is what we are talking about as a concerted step. When the abstraction of hydrogen and departure of leaving group takes place simultaneously, we call it as concerted step. And this step is found to be the slowest step and the rate determining step. Hence, you will see in a rate determining step there is both substrate as well as nucleophile present, so you call it as bimolecular reaction. Well, we are going to see the details of that. As of now, if hydrogen is lost from the beta dash carbon, meaning from the carbon which is more substituted or the carbon which is less acidic, the product obtained will be ZZEF elimination product or ZZEF elimination product. So 2-butene is major. But when the abstraction of beta hydrogen takes place from that beta carbon which is less substituted or more acidic H, the alkene obtained is known as Hofmann elimination product, which is the minor product. Now, like I said, in most of the cases, ZZEF elimination product is obtained to be or found to be the major product. However, there are going to be some circumstances, some condition where Hofmann elimination is obtained as a major product. We will be seeing it little later. As of now, let us focus on the detailed reaction mechanism of E2. So, we have got secondary alkyl halide treated with the strong base. So, strong base with respect to this alpha, let's call this is beta dash carbon and this is beta carbon. So, if base abstract the beta dash hydrogen atom, I'll call it as path A. And if it abstract the hydrogen from beta, I'll call it as path B. Abstraction of a beta hydrogen and departure of leaving group is taking place simultaneously in a slow step called as rate determining step. So now see here. Since ethoxide and beta dash hydrogen atom are in a process of formation of mu bond, there will be partial bonding here. Beta dash carbon and hydrogen, this bond is going to be broken. So there will be partial bonding here as well. Since this sigma bond is going to shift here to form double bond between alpha and beta dash, partial double bond character here, and carbon bromine bond is in a process of breaking, so partial bond will be existing here as well. So the transition state obtained can be shown like this. CH3, CH, H, new bond formation, single bond CH, new pi bond formation Br, and here CH3. So this is the transition state 1. Right, everyone? Similarly, if abstraction of a beta hydrogen taking place via path B, what are we going to get? The transition state corresponding to this can be represented like this. Look here. So we have got CH3, CH2, CH, and carbon bromine bond is in a process of breaking. Then we have got CH2 here. Since beta hydrogen will be abstracted, this bond is going to shift here. So partial pi bond character here as well. this bond is in a process of breaking. So we have got OET here as well. So that is also called as transition state 1. But yet again, like we saw in case of even reaction mechanism, this partial pi bond character is going to result in the formation of more substituted alkene. So the energy of this transition state is lesser. Hence this is more stable transition state. Because this is more stable transition state, the alkene formed from this transition state will be the more stable alkene. On the other hand, this is having a partial pi bond character between two such carbon, which is going to form less substituted alkene. So this is the less stable alkene, a less stable transition state. So the alkene formed from this transition state is going to be the less stable one. So okay, the product obtained would be CH3, CH double bond, CH and CH3. Whereas here, a fast step will result in the formation of less substituted alkene, that is 1-butene. Alright everyone, so two products obtained. The first one, more substituted alkene, is the Sedzeff elimination product. Second one is Hofmann elimination product. Now for this reaction, if you try to put energy profile diagram and find out some of the important characteristics reaction. First of all, let's have a look at the energy profile diagram. So when we are plotting the energies of reactants and product against the progress of reaction, we are getting a curve. What is that curve? Well, we had second dibutyl bromide here. As the base approached, because we had two different beta carbon atom, beta and beta dash, abstraction of a beta hydrogen from the beta dash carbon resulting in the formation of more stable transition state. So via path A, the transition state that we are getting is more stable. So via path A, the transition state we are getting is more stable, hence energy is lesser than the transition state via path B. So because transition state via path A is more stable, the product obtained will be more stable alkene, which is 2-butene than 1-butene. So after this reactant, you will see there are two curves you are getting, one with of lower energy of transition state, other of higher energy of transition state. Hence the corresponding product obtained are more stable and less stable respectively for path A and path B transition state. Now when you talk about rate expression, well, you can see in a rate determining step, both substrate and bases are involved. So the molecularity of reaction is 2, and experimentally determined rate expression, that is rate is proportional to molar concentration of substrate as well as base. Hence you can see rate is equal to K into product of molar concentration of substrate and base, meaning by altering the concentration of any of this, the rate of reaction will also be altered because it is directly related to it. That clearly indicates, now whenever you need a base, you will always need such a base which is a stronger base. So because it's a concerted step, E2 reaction will always take place in presence of strong base. And we have listed down 5 important strong bases. Guys, you'll have to remember those 5 stronger bases. Now, molecularity and order of reaction. Well, from the rate determining step we saw, molecularity of E2 reaction is 2. And from the rate expression we can see substrate to the power 1, base to the power 1. Meaning with respect to substrate it is first order, with respect to base it is first order, but overall it is a second order reaction. So, and it is a second order reaction. All right, guys. So that is rate expression. This is molecularity and order of reaction. This is the energy profile diagram. Now, the most important thing of E2 reaction is the stereochemistry of E2 reaction. Stereochemistry of E2 reaction, as in, we need to understand what is the required arrangement of the leaving group and the beta hydrogen to be abstracted, which is required as a necessary condition. So guys, before we enter into the stereochemistry, the 2 points which we have already studied, we are just revising here. What is Setzeff elimination? When abstraction of beta hydrogen atom takes place from more substituted carbon, that is less acidic H, forming more substituted alkene, is Setzeff elimination. And when the abstraction of beta hydrogen atom takes place from less substituted carbon, result in less stable transition state to form less stable or less substituted alkene, is called as Hofmann elimination product. Well, we have studied this. Yes, this is what we were talking about, stereochemistry of the beta hydrogen atom and the leaving group, which is a necessary condition for beta elimination to take place. So we say the beta hydrogen atom which is to be abstracted and the leaving group which is going to leave simultaneously should be anti-coplanar to each other. Now what does that exactly means? Let me show you using Sohor's projection. Anti-coplanar or anti-periplanar, you can say that way. Look, let's say now whichever group we have here, R1, R2. This is leaving group, this is hydrogen atom, R3 and R4. Now look, you will see here hydrogen and the leaving group are in the same plane. You can see that they have been represented on the normal line. Solid wedge bonds R2 and R3 are on the solid wedge or solid line bonds which are coming outside the plane of paper, whereas R1 and R4 are the group which are represented on the hatch wedge or a dashed line which are going inside the plane of paper. So when you say anti-periplanar or anti-coplanar, meaning both beta hydrogen atom and the leaving group should be in the same plane but anti to each other. So because these two normal line indicate that these bonds are both in the plane of paper, in the same plane of paper, beta hydrogen atom, this is carbon carrying leaving group alpha and this is beta. So beta hydrogen atom and leaving group are in the same plane but they are anti to each other. This arrangement is what you call it as anti-periplanar, and this is the essential condition for E2 reaction to take place. The anti-periplanar can be represented in several ways. This is one way in a Sohor's projection. Suppose we have to represent that in a Newman projection. So how do we represent in Newman? Let me show you. Let's say all right. Now this is the front carbon. So that is hydrogen atom, R2, R1, leaving group, R3, and this is R4. Okay, so now you can see once again over here, hydrogen and leaving group are in the same plane. If I consider this as a plane, both leaving group and hydrogen are on the same plane and they are anti to each other. So base can abstract this beta hydrogen atom with the simultaneous loss of a leaving group. Just like the base can abstract this beta hydrogen atom, sigma bond will shift with the simultaneous loss of a leaving group. The same thing you can also consider in cyclic structure as well. So let's say I am understanding anti-periplanar arrangement in cyclic structure. We can show it this way. Well, everyone look here. Now this is our leaving group. So the carbon carrying leaving group is the alpha. Adjacent carbon is beta. And even this is beta. Let's call it beta dash. Now at beta carbon also we have got hydrogen. At beta dash also we have got hydrogen. But our requirement is that the leaving group and the beta hydrogen to be abstracted should be anti-periplanar, in the same plane but anti to each other. Is this beta hydrogen anti to the leaving group? No, they both are pointing downward, both are below the plane. But beta dash hydrogen atom is anti to the leaving group. So the base will always prefer to abstract this hydrogen, which is anti to the leaving group. Alright guys, so always remember, these are the required stereochemistries of a substrate so that the beta elimination can take place effectively. So those were some of the important characteristics, and now we'll talk about the factors affecting the rate of E2. Well, as we saw, the product of E2 elimination is an alkene and the major product is more substituted alkene. So for alkene to be more substituted, the substrate should also be more substituted alkyl halide. That's why as the number of alkyl groups on the carbon carrying leaving group increases, the rate of E2 also increases. So there are two common reasons for rate of E2 to increase with the increase in the number of alkyl group at the carbon carrying leaving group. Number one, because for such more substituted alkyl halide, the product, the alkene obtained, will be more substituted alkene. Second, because there are more the number of beta hydrogen atom, the probability of for a base to abstract the beta hydrogen also increases. Hence we say, as the number of alkyl groups at the carbon carrying leaving group increases, the rate of E2 also increases, because in such case you get more substituted alkene. Second important thing, as the number of antipositions increases, the rate of E2 also increases. Now what does this mean, guys? Look, suppose if I take 3 examples. Let's say here we have a leaving group bromine. Okay. And here R1 and R2. This is one arrangement. Second arrangement is BR. R1 H. H and R2. Third arrangement is leaving group, let's say bromine. This is R1, hydrogen, R2 and hydrogen. Okay guys, let's see here. The second important condition is saying, that is with respect to factors affecting which is a substrate, is As the number of antipositions increases, the rate of E2 also increases. Now we know the fact, for effective E2 reaction to take place, the beta hydrogen in the leaving group should be anti-periplanar. So now I have got a carbon carrying leaving group, so this is alpha and this two adjacent carbon are beta. Let's call this is beta and this is beta dash. Everywhere it's the same. This is alpha, beta and beta dash. Here as well, alpha, beta and beta dash. Now guys, tell me, if the leaving group is represented on the solid line, solid wedge or you can call it, then at the beta carbon atom we expect hydrogen to be anti to it. So if leaving group is on the solid line, hydrogen should be on the dashed line or a hatch wedge line you can call, meaning it should be on this dotted line. Do we have at this beta hydrogen on the dashed line? No. So this hydrogen cannot be abstracted. We have got one more beta, but at this beta also hydrogen is not present on the hatch wedge. It is present on the solid wedge, meaning it is on the, this is not anti, it is on the same side. So even this H cannot be abstracted. So although the first substrate has two beta hydrogen atom, it is of no use. This will not undergo E2 reaction. So this will not at all undergo E2 reaction. Look at this now. With respect to alpha, bromine is on the solid wedge coming outside the plane of paper. So at the beta carbon, we want hydrogen to go inside the plane of paper. Yes. So this hydrogen can be abstracted by the base because it is anti to the leaving group. What about beta dash? At beta dash, we wanted hydrogen on the hatch wedge. Do we have H on the hatch wedge? No. So this H cannot be abstracted because this is also in the same plane as that of bromine. We want it to be anti. And finally here, bromine on the solid line, hydrogen at this beta is on the hatch wedge. This can be abstracted. And this hydrogen is also on the hatch wedge. Even this can be abstracted. So the rate of reactivity for the third alkyl halide will be the most as compared to second, as compared to the first. That's what the stereochemistry of the substrate makes an important point for substrate to undergo E2 reaction. Well, the next substrate, leaving group. We know the fact good leaving group always favors E2. So fluorine will be giving relatively lesser reactivity rate. Chlorine will give you relatively faster rate. Bromine will give you even faster reaction of E2, and iodine, being best leaving group among halogen, will give you the highest rate of reaction towards E2. The next important factor, everyone, is about the solvent. Well, tell me what kind of base we want for E2 to take place. E2 reactions takes place in presence of strong bases. And the strong bases that we have learnt here are 5 important strong bases. All are anionic. Alcoholic KOH, sodium methoxide, methoxide, tert butoxide and sodamide. Now imagine if the solvent taken is a polar protic solvent. So in polar protic, because hydrogen is attached to electronegative atom, that hydrogen can form a bond with this anionic bases, isn't it? If that hydrogen is forming a bond with anionic bases, then the bases will no more remain base, because abstraction of hydrogen takes place from that anionic atom only. But because polar protic solvent will capture the base and will decrease the basicity of strong bases, so no E2 can take place. Hence we must avoid polar protic solvent. So what kind of solvents are required? Yes, polar aprotic. So polar aprotic solvents favors E2 reaction. Nature of base, well, we have already mentioned strong bases. We can also note them down again. such as alcoholic KOH, from alcohol, what do you remember? Ethoxide. You can put any metal ion here, sodium or potassium. Just like ethoxide, we also studied methoxide. Just like methoxide, you need to remember tertiary butoxide. And then sodamide. And Na+. So strong bases such as alcoholic KOH, ethoxide, methoxide, tert butoxide, sodamide favors E2 reaction mechanism. Alright, so these were some important factors of E2 reaction mechanism. And now guys, just have a look at one question. The product of this reaction is, well, they have given us alcoholic KOH. The moment you see alcoholic KOH, this reminds you that it is a strong base. The elimination reaction which takes place in presence of strong bases, E2, is what we have seen just now. Now, the substrate is given. Carbon carrying leaving group is alpha. This is beta. And this is beta dash. Well, at both beta and beta dash, they have shown solid lines showing methyl. But if you look at this carbon, only 3 bonds can be shown. 1, 2 and 3. So the remaining third bond has to be hydrogen atom. So let's see if I represent that. It has to be on the hatch wedge because solid wedge is CH3. Remaining 2 bonds are the normal lines, normal bonds. At beta dash as well, 2 normal lines can be seen. Methyl is on the solid wedge, so the hydrogen has to be at the hatch wedge. And now when you carry out E2 reaction, the required stereochemistry is that beta hydrogen and the leaving group should be anti-periplanar. So if leaving group is on the hatch wedge, the beta hydrogen should be on the solid wedge. But at both beta and beta dash, solid wedge lines or the solid lines are occupied by the methyl. So although at beta and beta dash I have got 2 hydrogen atom, none of the hydrogen atom can be abstracted. So I will say no reaction will take place. Or rather no E2 reaction will take place. So which option is appropriate? Option C, no elimination reaction will take place. So guys, that was all about E2, bimolecular elimination reaction. Now let me take you back to one very important statement which I referred earlier. If you remember, we said whenever we have got alkyl halide containing 2 or more than 2 non-equivalent beta carbon atom, when we allow it to react with a stronger base, it gives you E2 reaction, and the 2 products obtained, one of which is Sedzeff elimination product, other is Hofmann elimination product. In most of the cases, Sedzeff elimination product is the major product and Hofmann elimination is the minor product. But we said earlier that under certain conditions, sometimes you will see Hofmann elimination product can also be obtained as a major product. So question arises, what are those conditions under which Hofmann elimination product, which is although less stable alkene, is obtained as a major product? So I am taking you to learn the condition for Hofmann elimination to take place. Guys, I am taking few seconds. I want you guys to go through this till then. Come on. It's a self-explanatory thing here. Come on, everyone. Okay, everyone, here we go with Hofmann elimination product. Well, we know the fact. What is Hofmann elimination product? A type of E2 elimination reaction in which less substituted alkene is obtained as a major product. We call it as Hofmann elimination product. Remember, such Hofmann elimination product to takes place as a or such Hofmann elimination product to be obtained as a major product. There are some requirement in the substrate. Those requirement in the substrate are, well, not only in substrate, even in case of base, the base has to be a bulky base. So among 5 strong bases, not to forget, the 5 strong bases that we have learned are, which one? Start from alcoholic KOH. Alcoholic KOH. From alcohol, you remember ethanol's conjugate base, methanol's conjugate base, and tert butyl alcohol, meaning tertiary butoxide. Tert butyl alcohol's conjugate base, meaning tert butoxide, and then sodamide. Out of these 5 bases, guys, we all are aware that tertiary butoxide is the bulkier base. So first condition, whatever kind of substrate you have, but if your base is bulkier, it will give you Hofmann elimination product as the major product. Second, when the leaving group is a poor leaving group such as fluoride or Nr3+, this is a very common condition which you will see many a times. Sr2+ is also poor leaving group, but you won't find any question related to Sr2+. The most common question related to Hofmann product would be if your base is bulkier irrespective how the substrate is. Second, if your substrate contain poor leaving groups such as F or Nr3+, irrespective of what kind of the base is given to you. So to understand, let's take an example here. Well, look at the reaction here. We have got tertiary alkyl halide, so carbon carrying leaving group. With respect to this alpha, this is the beta carbon, and this is beta dash. Even this is beta, but these two are equivalent, so I've highlighted only one. So you can see, now we have got a bulkier base. This is a bulky base. Okay. Now guys, since this is a stronger base, one thing is for sure, this is going to undergo E2 reaction mechanism, which is the concerted step. Meaning abstraction of a beta hydrogen and departure of leaving group is going to take place simultaneously. We haven't mentioned the stereochemistry, assuming stereochemistry is being satisfied. Right now the structure is in 2 dimensions. So we can assume that stereochemistry is satisfied. If you look at beta carbon, guys, isn't it a primary carbon? Yes, it is. So this is the least substituted. Beta dash carbon is more substituted beta carbon atom. Now, because this is more substituted beta carbon atom, when a bulkier base will try to approach that beta hydrogen atom, which is at the more substituted carbon, the steric hindrance will be experienced by such a base because this is a substituted carbon. But because this is a primary carbon, there are no bulkier group present around it, so the base will be able to conveniently abstract the beta hydrogen atom. So in other words, I can say the beta hydrogen atom is easily accessible beta hydrogen atom to the bulkier base than the beta dash because it is substituted carbon. There are some groups present around this beta dash. So approach of bulky base towards such beta hydrogen will be relatively difficult. Hence, base which is bulky will prefer to abstract the hydrogen from beta carbon atom in the major product. So the major product will be obtained when base is abstracting hydrogen from lesser substituted carbon or more acidic hydrogen atom. So the major product will be here. Let's call it path A. So the product via path A is CH3, CH2, CCH3 double bond CH2. Whereas if base abstract hydrogen from beta dash, then the product via path B will be more substituted. but it is difficult for bulkier base to abstract because it is not easily accessible hydrogen atom. Right? CH3, CH3 carrying methyl and another CH3. So in this case, which is major? Hofmann elimination product is the major product, because this alkene is obtained by removal of more accessible H. This is the minor one. Alright everyone, so that was condition when the base is bulkier. Second condition, when you have got poor leaving groups such as F. Okay, before that let's solve some question here. So simply now you have to write down the major product. Okay, we'll be writing only the major product. So what will you do? You will look at the base which is bulkier. If this is bulky base, then you're going to carry out Hofmann elimination. So carbon carrying leaving group is alpha. This is beta. This is beta dash. So beta dash is more substituted. Beta is relatively less substituted. So easily accessible hydrogen is from the beta carbon. So base will prefer to remove hydrogen from beta carbon. Right everyone? So double bond between beta and carbon carrying leaving group. So the product obtained will be over here. Right? That was the beta which was relatively less substituted. See, this is secondary carbon, this is tertiary. So secondary carbon is relatively less substituted than tertiary. Hence easily accessible hydrogen atom. Now over here, carbon carrying leaving group. So adjacent carbon is beta, and this adjacent, let's call it beta dash. Beta dash is primary, beta is tertiary. So this is more sterically hindered hydrogen or carbon, and this beta dash carbon is the one which is primary, and hence hydrogen from beta dash will be easily accessible. So base will prefer to abstract hydrogen from beta dash. So the product obtained would be and then we'll get double bond formation here. So these are the major product obtained by Hofmann elimination. Second condition was presence of poor leaving groups such as F, Nr3 plus and Sr2 plus. Let's take an example here. See, we have got secondary butyl fluoride. So fluorine is a poor leaving group. We'll just note it down. F is poor leaving group. Okay. Now for our convenience, let's say if I highlight one of the beta hydrogen. So this is carbon carrying leaving group alpha and this is beta. This is beta dash. Okay. Let's say I'm highlighting one hydrogen here and one hydrogen here as well. Now see, when your leaving group is a poor leaving group, irrespective what kind of base you have, still it is going to give you Hofmann. And why it is so? Imagine if your base is abstracting the hydrogen atom, let's say from beta carbon or from beta dash carbon. So strong base will immediately abstract the hydrogen atom. But after loss of this hydrogen atom, what do we expect? The sigma bond to shift here towards alpha and leaving group to leave. I repeat, because the base is stronger base, it immediately abstracts the beta hydrogen. Then we expect the sigma bond to shift towards alpha and alpha to leave the fluorine group immediately. But we know the fact fluorine is a poor leaving group. So after loss of hydrogen, when sigma bond would want fluorine to push ahead and to leave the alpha carbon, it is not going to leave. So such sigma bond, instead of getting delocalized between beta dash and alpha, it remains on the beta dash carbon for a while, but sometime it resides on the beta dash carbon. Similarly, if abstraction of hydrogen will takes place from beta hydrogen atom, this sigma bond won't shift directly between alpha and beta, because this is poor leaving group which is going to take time to leave. So this bond pair is going to reside on the beta carbon. which means momentarily there will be development of carbon ion at beta dash as well as beta carbon. Let me show you that. So momentarily here there are carbon ion character developed. Of course, this is going to be present for a very small fraction of time, not for a longer time. Hence, I'm putting this in a square bracket, indicating that this is highly unstable. But when you look at this carbon ion character, tell me this carbon ion has only one alkyl group present and one minus I of fluorine. So, donation effect, electron donating inductive effect will increase the electron density on carbon ion, which is what we call it as accumulation of charge. If accumulation of charge or electron density increases, the stability of conjugate base decreases. So this is going to be less stable carbon ion. But in comparison to this carbon ion, for this carbon ion we have got two alkyl group. So when two alkyl group will show electron donating inductive effect, electron density on the secondary carbon will increase even more. So more the charge, more the accumulation of charge, lesser stable will be the carbon ion. So this carbon ion is going to be less stable, and hence the primary carbon ion is relatively more stable. More stable the carbon ion, more stable the conjugate base, stronger the corresponding acid. Hence we have been referring the beta carbon carrying more number of hydrogen as more acidic hydrogen atom. So because this is more stable, this will delocalize and slowly F will leave. So now think in this way. If the base has got options of abstracting two hydrogen atom, preferably from where will it abstract? If it is going to acquire partial carbon ion type character, of course, between the two beta carbon, base will prefer to abstract hydrogen from that beta carbon whose carbon ion is relatively more stable. Hence, the abstraction of hydrogen takes place from the carbon, which is the less substituted carbon or more acidic hydrogen, which is going to give you major product as Hofmann elimination product. So now this will immediately form an alkene between first and second carbon, bonded to CH2 and CH3. Alright everyone, so that is your product. So you saw, when your base is bulky, you're going to get Hofmann elimination product. When your leaving group is a poor leaving group such as F, you are still going to get a Hofmann elimination product. And now the important condition is presence of Nr3+. Well guys, pay attention to this, what I'm saying. If you ever find that you have got quaternary nitrogen atom with OH minus ion as a base and heat, it is always going to be a Hofmann elimination product. Now let me tell you, what are the different ways by which generally they can give you this base. One is they'll give you directly OH minus and heat, or they might also give you AgOH and heat, or they might say moist Ag2. And heat. So moist Ag2 is what? Ag2O in water. Ag2O plus water, if you write down its reaction, you're going to get 2 AgOH. So it is eventually nothing but AgOH and heat. AgOH is nothing but OH minus and heat. And that's why any of this condition eventually tells us that these are the condition for the Hofmann elimination. Either of these three. Now, since we know that this is going to give you Hofmann elimination is a type of beta elimination. So what I will look for, if this is a quaternary ammonium ion, which is the derivative of ammonia, so this is your functional group. Carbon next to that is your alpha. So this is alpha, this is alpha, this is alpha, this one is alpha, and this one is beta. So guys, Hofmann elimination is a type of beta elimination, meaning you should look for abstraction of hydrogen from which carbon? Beta carbon. So for these three alkyl, we don't have beta carbon at all. So no question of abstraction of beta hydrogen. So here we have only one beta carbon. You may have a substrate where there will be more than one beta carbon atom. When you have a substrate such as quaternary ammonium ion containing more than one beta carbon, and when you have to do Hofmann elimination, in that case you should look for that beta carbon which contain more number of hydrogen atom or more acidic hydrogen. Right now we are not left with any option. This is the only beta carbon. So what will we do? Look, let me highlight one of the hydrogen. Let's say this CH2 I'm writing like this. I've erased this 2. I'm putting one H here. Now since reaction is in presence of OH minus, everyone's here. So base abstracted the beta hydrogen atom. So this bond will break. Now we'll have to always delocalize the sigma bond between, or you can say towards, alpha carbon atom which is connected to nitrogen. When base has abstracted beta hydrogen. Why beta hydrogen? Because I saw Nr3 plus and OH heat, meaning it is Hofmann elimination. Hofmann elimination is a type of beta elimination, right? So if this is beta elimination, you should abstract the beta hydrogen. Out of this, I could only see beta hydrogen present here. So base abstracted beta hydrogen. Now the sigma bond should go towards alpha carbon which is directly connected to N. Because when the sigma bond will shift here, you are going to get double bond here. So valency of this carbon will become 5. So this sigma bond will break towards nitrogen in order to maintain its tetravalency. So the product obtained will be CH3 CH double bond CH2. Plus nitrogen will carry lone pair and 3 methyl groups. Right, everyone? So this is going to be your Hofmann elimination product. Now guys, you may have a several condition of Nr3 plus. Let me just take one example. Let's say we have got a compound like this. CH3, CH2, NH2 and lone pair. Upon arrow, they have mentioned first condition as methyl bromide in excess and second condition is OH minus and heat. Now understand one thing, methyl bromide is given in excess, meaning as many replaceable hydrogen atoms we have, all will be substituted by methyl. The process is called as methylation. So I'm telling you a simple trick what you have to do. You have to count the replaceable hydrogen atom at nitrogen plus 1 for the lone pair. So total number of methyl bromide you will need for the methylation of this NH2 is 3 methyl bromide. And how do I know that? Because in this amine I have got 2 replaceable hydrogen and 1 lone pair. Total 3. That's how 3 methyl bromide will react with this and your product will be, now this CH3 deliberately I'm writing it as CH2H followed by CH2 single bond N. First one H got replaced by methyl, so that was methylation. Second H replaced by methyl, so methylation, and the third lone pair donated to methyl, and that's how you got quaternary ammonium salt. Now you got Nr3 plus. So that's why if you have got primary amine given and methyl bromide is given in excess, which means as many Hs plus 1 lone pair can be substituted by methyl group to give you quaternary ammonium ion. And now second condition is OH minus and heat. The moment you see that you have got Nr3 plus, OH and heat, meaning the next step is certainly going to be Hofmann elimination. Now OH minus and heat would be, if we have got OH minus, Nitrogen, next carbon is alpha, even this is alpha, even this is alpha. A carbon here is alpha and this one is beta. The base can abstract the beta hydrogen. I told you when H is lost, sigma bond of beta carbon shifted towards that alpha which is connected to nitrogen. If this bond shifts here, this carbon is going to be pentavalent. So this bond has to break towards nitrogen to give you tertiary amine. So this is resulting in the formation of CH2 double bond CH2 here, and the nitrogen is further carrying a lone pair N carrying 3 methyl groups. Okay everyone, so that's how, if you don't directly have quaternary ammonium ion, if they have given primary or secondary amine whatever, if methyl bromide is given in excess, then you have to do exhaustive methylation. Exhaustive methylation meaning as many methyl can be introduced on nitrogen, you have to get those. How do we get that? Simple trick is, I will look for how many replaceable hydrogen. I have got 2 replaceable hydrogen plus 1 lone pair. So total 3 times methylation will take place. So at the nitrogen I'll get 3 methyl other than the existing alkyl which was ethyl. Then upon heating with OH minus ion, you're going to get the final alkene plus the tertiary amine. Sometime you may have a question like this. Suppose if I have some cyclic structure like this. Everyone here, let's say we have been given cyclohexylamine. Again, the condition given here is methyl bromide in excess and moist Hg2O or HgOH and heat or OH minus and heat. So first thing what you'll do, since it's primary amine, with excess of methyl bromide, how many methyl will be introduced here? 2 hydrogens plus 1 lone pair, that is 3. So we will be getting NCH3 thrice plus. So that is your NR3 plus. Now OH minus and heat is Hofmann elimination. So Hofmann elimination is a type of E2. E2 is a type of beta. So you look for beta carbon, nitrogen, and this is alpha. I've got this is also beta and even this is beta. Let's call it beta dash. Now I'll highlight 2 H's from one of the beta. See, both beta are equivalent. So base can abstract hydrogen from any of this carbon. Let's say base abstracted this hydrogen. So sigma bond, I told you, hydrogen, the sigma bond of beta hydrogen you should shift towards alpha, which is further connected to nitrogen, so that this bond can break. So this will leave and this will result in the formation of, now this bond shifted here, we got double bond plus tertiary amine, where nitrogen will carry lone pair with 3 methyl groups. Alright guys, so if any such question is given, look for how many replaceable hydrogen we have with methyl bromide or any iodide in excess or maybe any other alkyl group. Carry out that exhaustive alkylation and then carry out Hofmann elimination to get corresponding products. That is how you may have question on Hofmann elimination. And now finally we compare the substitution and elimination reaction. Many a time we see the questions have been asked in such a way that we get confused whether we are supposed to carry out SN1 or SN2 or E1 or E2. So basically this simple trick helps us to identify which mechanism it is going to undergo. So guys, remember when you talk about, let's say here we have got SN2 Here we have got E2. Here I'm comparing SN1 and here E1. I want you guys to remember the key feature of all the reactions. So SN2, what is the key feature? It's a concerted step. For E2, what is the key feature? Concerted. Simultaneous. Just that here, simultaneous attack of a nucleophile and departure of leaving group. In E2, simultaneous abstraction of a beta hydrogen and departure of a leaving group. Right? SN1, what is the key feature? Formation of carbocation. Formation of carbocation. Even also proceeds via formation of carbocation. Right? Now let us talk about the important feature, substrate. Well, SN2 is concerted, meaning you need strong base and the nature of substrate would be less sterically hindered. So here we will have methyl halide, then primary alkyl halide, then secondary alkyl halide. Most reactive will be methyl halide, then primary alkyl halide and secondary. Tertiary won't give you SN2, right? When you talk about substrate, the factor substrate towards E2, the most reactive substrate towards E2 is tertiary, then secondary, and then primary. No question of methyl halide because methyl carbon itself does not have any beta carbon. Methyl halide does not have a beta carbon, so won't give you E2, which is type of beta elimination. Right, everyone? Nucleophile. Well, for SN2 to take place, we need strong nucleophile. Strong nucleophile meaning anionic. Right? For E2 to take place, we need stronger bases. Just now we saw 5 bases, you all will have to always remember. So strong base. Which strong bases? Let's write it down. First one, you start with alcoholic KOH. From alcohol, you remember ethanol's conjugate base, that is ethoxide. From alcohol, you also remember methanol's conjugate base, that is methoxide. You also remember tertiary butyl alcohol. So tert butyl alcohol's conjugate base, and finally soda-amide. Okay, everyone, see, we are revising the entire, all the 4 important mechanisms here. Leaving group, this has to be universally good leaving group. Good leaving group, and this is going to be common for all the mechanisms. So here also you'll need good leaving groups. Solvent, if you need nucleophile to be strong enough, meaning you don't want this to be captured by the solvent, meaning the solvent should not be polar protic. So for SN2, the favorable solvent is polar aprotic. Polar aprotic. Here, again for E2, you need stronger bases. All are anionic, you see that. Which means again you don't want them to be captured. So here as well you will need polar aprotic. Polar aprotic. Alright. SN1 reaction and E1 reaction. We know that all the factors remain same. The only differentiating factor is temperature. So I think this is going to be easier one. Substrate. Because SN1 involves formation of carbocation, the substrate which can form stable carbocation will have a faster rate, meaning tertiary alkyl halide. will be fastest reactive, then secondary, and then primary. Methyl halide won't give you SN1 type of reaction. Similarly for even, yes, the order of reactivity of substrate is tertiary alkyl halide, most reactive, followed by secondary alkyl halide, and the least reactive will be primary alkyl halide. But because SN1 and even results in the formation of carbocation, we should always keep one factor in mind. If there is requirement of carbocation rearrangement, we must always do carbocation rearrangement first. Nucleophile in SN1. Well, in SN1, the rate expression says rate is directly proportional to molar concentration of only substrate, no nucleophile. So you don't need any anionic nucleophile. So solvent itself acts like a nucleophile. So you can say weak nucleophile. In brackets, solvent itself. Solvent itself. For bases also, weak base. Weak base meaning solvent itself is going to act like a weak base. Solvent itself. Leaving group, as we have said, it has to be always a good leaving group. Good leaving group will favor SN1 because you want carbocation to be formed faster. Similarly in even, there is involvement of formation of carbocation, so this also has to be a good leaving group. Alright, solvent in SN1, there is a formation of carbocation, so polar protic solvent will favor the formation of carbocation with its high dielectric constant. So you'll need polar protic solvent. Polar protic solvent. And other important facts about the solvent is, because it is polar protic solvent, it will also stabilize the carbocation which is formed. So here as well, because carbocation formation takes place, we want polar protic solvent. And the only factor that differentiates between SN1 and even is the temperature. So elimination reactions involve more breaking of a bond than SN1, so need higher temperature. So higher temperature favors even. High temperature will favor even reaction. Alright guys, so this is how we simply compare substitution versus elimination. So if any question comes and where you are in dilemma to decide what mechanism it is going to undergo, simply you'll have to recall this 4 mechanism like this, which is the comparative studies of all the substitution, the most important substitution and elimination reaction will help you out to decide the precise mechanism. And now guys, the last part of this which we have to learn today is E1CB, unimolecular elimination via conjugate base. Okay, now what exactly is this E1CB? Let me just make you understand this. Let us assume that we have got a substrate like this. You see, we have got a poor leaving group here. So the carbon carrying leaving group is alpha, adjacent carbon is beta, and adjacent to this beta carbon we have got presence of electron withdrawing group. So far in the substrate what we have observed is we have got poor leaving group F, and adjacent to beta carbon we have got electron withdrawing group. So these are the two important conditions that we have observed in the substrate, and I'm allowing it to react with, you see, we are allowing it to react with ethoxide. Well, this is C2H5O minus. So not to forget, ethoxide is a strong base. Now because ethoxide is a strong base, what will it do? it will immediately a fast abstraction of beta hydrogen atom. But after fast abstraction of a beta hydrogen, we expect the sigma bond to shift between alpha and beta, and it should push the fluorine to leave as a good leaving group. But because fluorine is a poor leaving group, this sigma bond will reside on the beta carbon atom. And this is also favored because as soon as this bond pair will localize at this beta carbon atom, there is adjacent electron withdrawing group which will withdraw that electron pair and stabilize that carbon ion. So the carb anion which is obtained can be stabilized by resonance. Such carbon ion is a stable conjugate base. Hence, here after abstraction of beta hydrogen atom with a strong base, I am going to get a stable conjugate base. So I'll just put it down. pH C double bond O CH electron pair minus. This is the fast abstraction, by the way. This is the fast step. So this is not the rate determining step. You got carbon in here, then CHF and CH3. And CH3. Well, this is the stable conjugate base. So I'll just mention that this is conjugate base. Guys, C dot B meaning I'm talking about this is the conjugate base. Now once the conjugate base is formed, now slowly the electron pair will delocalize and poor leaving group will slowly leave from here. So this step is going to be the slow step. Yes, and if this is a slow step, guys, what do we call it such step? Rate determining step. So this is the slow step, which is the rate determining step. So what is happening? Upon departure of fluorine, you will get formation of double bond here. So pH C double bond O CH double bond CH further connected to CH3. Right, everyone? So see what happened. We had a substrate containing poor leaving group and electron withdrawing group adjacent to beta. Another requirement, we needed a strong base because strong base immediately it fast abstract the beta hydrogen atom, resulting in the formation of a stable conjugate base due to presence of electron withdrawing group. Such a stable conjugate base then slowly allow leaving group to leave in a rate determining step to result in the formation of a product. So a type of elimination reaction begins with the rapid loss of proton to a strong base. Yes, we saw that it's a fast step. A loss of proton leads to a stabilized carbon ion, which is the conjugate base. In even CB reaction, the formation of carbon ion, meaning conjugate base intermediate, is fast, and the loss of leaving group is a slow step, meaning it is a rate determining step. Right? So this is what we have seen. So guys, from this, for even CB, we will come to that point. Why are we calling it as even CB? Okay. Before that, let's understand the conditions required for this even CB to take place. Number one, your substrate should have poor leaving group such as F. Number two, there should be electron withdrawing group present attached to the beta carbon. Number three, you need a presence of a strong base. So these are the conditions: presence of EWG at beta carbon, poor leaving group such as F, and preferably in presence of strong base. Now guys, suppose if I want to derive the rate expression, the rate is proportional to molar concentration of, you see that here, rate is proportional to, according to the according to the reaction mechanism, rate is proportional to molar concentration of conjugate base. Hold on everyone. Which means rate is equal to K into molar concentration of conjugate base. Let's call this is equation number 1. Whereas if you see, conjugate base formation is obtained as an equilibrium reaction between the substrate and the strong base. So if I want to find out the concentration of conjugate base, I'll have to find out the equilibrium constant first. So I will say K equilibrium is equal to the ratio of molar concentration of product to the molar concentration of reactant. Guys, you have studied that if you have got equilibrium, how do you find out equilibrium constant? So equilibrium constant K equilibrium is equal to ratio of molar concentration of product. For this equilibrium, what is the product? Conjugate base. To the molar concentration, to the product of molar concentration of reactants. What are reactants? Base and the substrate. So if I want to find out the equilibrium constant, I will say K equilibrium is equal to molar concentration of product, which is the conjugate base, upon product of molar concentration of substrate into strong base. Right? Now since I want to find out the value of conjugate base, I'll keep numerator here, and whatever value in the denominator, if I bring it to the right, I will get writing expression in terms of conjugate base. So molar concentration of conjugate base is equal to K equilibrium into molar concentration of substrate into molar concentration of base. Now substituting this value in equation 1. Substituting in equation 1. What will we get? R will be the rate constant R of E1CB is equal to K into the value of conjugate base is this whole thing, meaning again you have got K equilibrium. Okay, let me put it. K equilibrium into molar concentration of substrate into molar concentration of base. Now this K, which is a constant, and K equilibrium is again equilibrium constant, so product of two constant will be a new constant, so you can write it as R is equal to new constant, let's call it as K dash, into molar concentration of substrate into molar concentration of a base. So this is your final equation or a rate expression, which means rate of E1CB is directly proportional to, if I convert this equal to sign and constant into proportionality, I can say rate is directly proportional to the product of molar concentration of substrate and a base. Now guys, if you talk about the molecularity, and the order of reaction, guys, molecularity you get from what? Rate determining step. In rate determining step, only one molecule is involved, that is conjugate base. Hence it is unimolecular. Because it is unimolecular, you call it as even. And what is that molecule? Conjugate base. So you are calling it as E1CB, a unimolecular reaction. Unimolecular reaction where the rate of the reaction is depend upon the concentration of only one molecule, which is conjugate base, is called as E1CB. So molecularity of reaction is 1. But order of reaction, if you see this final expression, substrate nothing written meaning substrate to the power 1, base nothing written meaning base to the power 1. So E1CB is unimolecular individually with respect to substrate. I'm saying E1CB reaction is first order with respect to individual substrate, and again first order with respect to just a base, but overall I can say it is second order reaction because substrate to the power 1, base to the power 1. So overall second order reaction with respect to substrate and base both. So overall second order. So remember, in JEE you may have a question. Molecularity of E1CB is 1, but it is overall second order reaction. First order with respect to substrate, because power is 1, and first order with respect to base, but overall it's a second order reaction. So that is all about E1CB. These are the required condition. Just to take 2 examples to give you completion to this E1CB. Let's say we have been given this kind of substrate. So condition is what? Substrate should have a poor leaving group F, and you should have at the beta carbon there is electron withdrawing group. So yes, this are electron withdrawing group, and you need strong base. So strong base will abstract hydrogen from beta carbon, right? The sigma bond will localized at the beta carbon for a while. So we will be getting chlorine, carbon, chlorine, conjugate, base, bonded to C, carrying 3 fluorines. Then slowly, in a rate determining step, the negative charge will delocalize and one of the fluorine will leave. So upon departure of fluorine, you will be getting double bond here. So chlorine bonded to carbon, doubly bonded to another carbon carrying 2 fluorine. Here, carbon carrying poor leaving group alpha, adjacent carbon beta. To this beta, there is whole phenyl ring with nitro group at para position. So this entire is electron withdrawing group, right? This entire is EWG. So what base will do? Abstract the beta hydrogen. Sigma bond will localize on beta carbon for a while. So the first step is a fast step. Resulting in the formation of a conjugate base. Like you can see here, there was formation of conjugate base. Right? Here as well, you will get conjugate base at beta carbon. So if I write it down. CH electron pair minus, and then alpha carbon carrying F here. Now what will happen in a slow step, in a rate determining step? What will happen? The negative charge will delocalize, which will push away the poor leaving group F slowly. So we'll be getting double bond over here. Right everyone? So phenyl ethene carrying nitro at para position. So we will have nitro, phenyl ring with CH double bond CH2. That's your product. So guys, those are a few examples of E1CB. Such a wonderful session it was. Guys, what all we have learned in this session, let me tell you. We started our discussion with elimination reaction. We studied unimolecular elimination. Then we studied bimolecular elimination E2. And in the previous class, we had discussed all the nucleophilic substitutions. So we compared substitution versus elimination. We understood all the important conditions and those differentiating point in every mechanism. And then finally, we also studied E1CB, unimolecular elimination via conjugate base. I'm hoping that you guys have understood what we have learned today, and you guys are putting a lot of efforts to make sure that you bring out best that you have in you guys. So I wish you the same, and I wish you all the best. Take care. I'll see you soon in the next class with respect to the physical properties of haloalkanes and haloarenes, some simple classification of haloalkanes and haloarenes, and then we'll certainly begin with methods of preparation of alkyl halide. So I'll see you soon in the next class. Thank you so much everyone.